Assalamualaikum warahmatullahi wabarakatuh. My name is Azira binti Hamzah. Me and my group members, which are arbaenah, Muhammad afiq and megat, will present to you the non-ideal flow reactors. So on this slide, we are gonna explain about introduction, basics of non-ideal reactors, application of the equipment. So for the introduction, in non-ideal reactors, different flow effects can occur. These effects can influence the ideal behavior strongly or weakly. They can affect the reactor design, the yield, or the temperature development of a chemical process. Non-ideal reactors are reactors that do not follow the models we have developed for ideal CHE244, BFRs, and PBRs. So let's learn the basics. So basic of the non-ideal reactors, we have resident time distribution or RTD, state of aggregation of the flowing stream, and number 2, state of aggregation of the flowing stream, and the last one is earliness of mixing.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad afiq bin Jamaluddin. So for this presentation of basics of non-ideal flow reactors, I will discuss about state of aggregation of the flowing stream. State of aggregation of the flowing stream. It means its tendency to clump and for a group of molecules to move together. One of the three or more fundamental forms, conditions, or states of matter that are commonly considered to include the solid, liquid, and gaseous forms, and often others, such as the colloidal. Flowing material is in some particular state of aggregation, depending on its nature. In the extremes, these states can be called microfluids or macrofluids. State of aggregation can be clarified into two systems: single phase system, and the second one is two phase system. So this is a single phase system, where this is two extremes of aggregation of fluid. So this is a microfluid, it is a gaseous and ordinary, and it's also not very viscous liquids. Individual molecules are free to move about and intermix. Okay, next, this is a microfluid. It is a non-coalescing droplets and solid particles, and it is very viscous liquids. Molecules are kept grouped together in aggregates or packets. So this is a two-phase system. In this diagram, this is a Sparger reactor, which it contains gas bubbles in the state of liquid. Here, gas is a macrofluid, while liquid is a microfluid. The next one is spray tower reactor. It contains liquid droplets in the state of gas. Here, gas is a microfluid, while liquid is a macrofluid. Next diagram is a bubble column, where the gas here is a macrofluid and liquid is a microfluid. The next one is a spray tower. The gas here is a microfluid and liquid here is a macrofluid. Okay, that's all from me for this presentation. Thank you.
Residence time distribution is process need to conduct for this non-ideal reactor, because some of the reactant will not react completely in the reactor. And next, channeling of fluid. The channeling of fluid is backpacking of the catalyst, and then short circuit. Short circuit is some reactant that will flow straight into the output of the reactor without react with any reactant in the reactor. And lastly, creation of stagnant region in the vessel. Okay, the stagnant region is some space that the reactor will not react in the reactor. Okay, and next is the example of resident time distribution of a gas liquid system. The gases reactant A was bubbled into the reactor while the reactant was fed through an inlet tube in the reactor side. Okay, as you can see, the gas A will get into the reactor from the bottom of the reactor, and liquid B will be sent from the left bottom of the reactor. So gas A will react by liquid B with the bubble by using bubble process, and then the liquid of the main bottom of the reactor will produce the product of reactant A and B. And that's the reaction took place at the gas liquid interface of the bubble, and the product was the liquid simultaneously, which will be regarded as perfectly mixed. Okay, next, for the PET reactor. The reactor is packed with catalyst so that the reacting fluid usually does not flow through the reactor uniformly. Okay, as you can see from the diagram, the reactant will insert from the left of the reactor, and then it will flow through the catalyst inside the reactor. But as you can see the arrow, the reactant will not flow finally because of some catalyst in the reactor. There may be section in the pack bed that give little resistance to flow. As a result, a major portion of the liquid may channel through this pathway. So the molecule flowing this pathway does not spend as much time in the reactor as those flowing through the region high resistant to flow. And lastly, the CHE244. The CHE244 reactor is the inlet and outlet. Pipes are close together in many CHE244 reactors. In addition to short circuiting, stagnant region are often encountered. In this region, there is little or no exchange of material with the well-mixed region, and no reaction occurs. Okay, this means that CHE244 also have short circuit process, and then the stagnant region will be collected from the dead zone.
The last one is earliness of mixing. So, the fluid elements of a single flowing stream can mix with each other either late or early in their flow through the vessel. So, as you can see, these three are the example of single interly flowing fluid. For the early mixing, we can see the mixing will occur at the early region of the vessel. So, in this region, you can see the lots of mixing of young and old fluid. But at the region that don't have any mixing, will have the flat velocity profile. Next is uniform mixing. Uniform mixing have the same along the whole vessel, so there is no different in any region because it is uniform. So the late mixing, at the beginning area of the vessel, there is no mixing of young and old fluid, because when we do the late mixing, the mixing will occur at the end of the area of the vessel. So this gonna be the well mixed region on the mixing. This is the example of two entering flowing fluid. The first one is a single entering flowing fluid. So for the two entering flowing fluid, two fluid will get into the vessel at the same time. So with this example, we can see A and B will enter the fluid at the same parallel flow. So the entry will get well mixed. So in this region, we can see that A and B have a lot of time for reaction. Then the second example, where the A and B flow into the vessel in the separate parallel, so the A and B will unable to react. So mixing only occur at the exit level and no time for reaction. So usually the earliness or lateness has little effects on overall behavior for single flowing fluid. However, for a system with two entering, reactant stream can be very important. So earliness or mixing often depends on the time for reaction, T reaction, the time of mixing, T mix, and the time for stay in the vessel, T stay.
Assalamualaikum madam, my name is Arbaenah and I am going to present on application of non-ideal flow reactor. So, for the application of non-ideal flow, here I give the two examples. First, the continuous third tank reactor, and second is the plug flow reactor. Okay, so actually, non-ideal flow is the flow that happen in the real reactor that is being used in the industries. So, here I'm going to explain on what happened in the CSTR and plug flow, and it is actually the non-ideal flow. So in the CSTR, the high concentration of the reactant at the feed entrance means that in the CSTR, the concentration of the reactant at the feed entrance is high, and then in the dead zones, the concentration is low, and the dead zone is usually at the corners and behind baffles of the reactor. So as you can see in the diagram, you can see the location of the dead zone. So it is at the corner. So that is where the low concentration is occur, and it is what happened in the real CSTR that is being used by many industry. And then the second one is what happened in the plug flow reactor. Okay, so for plug flow reactor, molecules move with changing speeds and in different directions due to fluid velocity profiles, turbulent mixing, and molecular diffusion. So this is the non-ideal flow in the plug flow reactor, and as you can see in the diagram, there is example for the channeling and how the flow or the molecules move in the plug flow reactor. So it is said that the non-ideal flow is happen in the real third tank, in the real continuous third tank and the plug flow reactor. Okay, so next there are also the residence time distribution models, where it characterizes the main flow features in non-ideal flow reactors. Okay, so these models is very useful to determine the mixing behavior and the conversion rate of a reactor system. Okay, so what is RTD models? It is for there to study or for there to calculate the for them to know the flow features in the non-ideal flow reactors, and it is being used by a lot of researchers or to characterize the main flow features in the non-ideal reactor. So the first one is the multi-parameter model, because there is the one parameter, double parameter, and multi-parameter model. So multi-parameter model is a combination where individual reactor models such as plug flow, dispersed plug flow, and mixed tanks were used. And the models are connecting the individual reactors by branch in parallel, in series, recycle, or cross flow. This is how they set up the reactors, or how the position of the single reactors becoming the multi-parameter model. Okay, so the last one is multi-parameter model is a model that were found to describe the real situation sufficiently. It means that it is a model that can describe the real situation of non-ideal flow sufficiently. Okay, so the second one is the tanks in series model. This model connects several ideal stirred tank reactors in series form, and then the total volume is distributed across the reactors. Okay, this model can be used whenever the dispersion model is used, and for not too large deviation from plug flow, both models give identical results. Okay, so the last one is the dispersion model. This model describes the deviations of the flow profile of a flow reactor from the ideal plug flow by adding a diffusive axial transport. Okay, so you can say that the tanks in series model is used with this dispersion model, and both models give identical results. So that is the RTD models, and I guess that's all from me and my group. Thank you, madam.